All right, so here's the second part of today's lesson, and we're going to talk about something called critical points. So critical points are x values where the derivative equals 0 or does not exist. These are important because they might be extrema. In other words, they might be places where you have maxes and mins. So let's take a look at why that's true. If you think about, typically when you have a maximum or a minimum, you have a place where the tangent line is horizontal, and that means the tangent line would have a slope of 0, so that would be where the derivative equals 0. You could also have a place where maybe there's a point or a cusp, and in that case, the tangent line can't really be drawn. There's not one unique tangent line, so the derivative does not exist. Now it's possible to have a function that has a place where the derivative equals 0 or does not exist, and that place is not actually a max or a min, like if you had a function that did something like this and happened to have a horizontal tangent line there. Sorry, it's kind of hard to make that look right, but something like so, let's say. There wouldn't be a max or a min there, but these are places where you might have a max or a min. Okay. So we're going to find the critical points of this function, f of x equals x to the negative first power minus x to the negative second power. We might see this function written this way, f of x equals 1 over x minus 1 over x squared, but it's definitely easier to differentiate if we have it written with just the exponents. So to find the critical points, we're looking for the numbers where the derivative of the function equals 0 or does not exist. So we find the derivative. So we get negative 1 times x to the negative second minus negative 2, so plus 2 times x to the negative third. Now let's change this back into more of a fraction form. So this is negative 1 over x squared plus 2 over x cubed. And then let's get a common denominator. So if we multiply the first fraction by x over x, we will have a common denominator of x cubed. So we have negative x over x cubed plus 2 over x cubed. So that could be thought of as 2 minus x over x cubed. Now, it's important when you have fractions to combine them into a single fraction, because if you want to know where this equals 0, you look for where the you look for where the numerator is 0. So 2 minus x equals 0, x equals 2. If you want to know where does the derivative not exist, you look for where the denominator is 0. A cube rooted both sides and got x equals 0. So the critical points, the x values of the critical points are x equals 2 and x equals 0. Now actually x equals 0, if you think back to the original function, is not even in the domain of this function. Okay, let's do another one. Find the critical points of this function, so something trigonometric. So again, we start with the derivative. The derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. So we want to know where that equals 0 or does not exist. Now, the cosine function is defined for all real numbers, as is the sine function. So there's no place where it does not exist. So we're just going to solve where this derivative equals 0. And to do that, I'm going to add cosine of x to both sides. Add sine x to both sides. And then I'm going to divide both sides by cosine x, because I remember that sine of x over cosine x is tangent x. So tangent x equals 1. So we need to find the places where the tangent is equal to 1. And if you remember your exact values, if you have a 45-degree angle, then you have a 45, 45, 90 triangle with sides 1, 1, square root 2, so the tangent is 1. Also, in the third quadrant, -1 over -1 for opposite over adjacent is also 1, so it could be 45 degrees or it could be 225 degrees. Now let's put those in radians. So if x is 45 degrees or 225 degrees, that's the same thing as saying that x is pi over 4 radians or 5 pi over 4 radians. But notice that we weren't given any kind of interval here, so we're actually looking for all of the infinitely many answers. And if you were to go around the circle again, you would get another answer, and again, another answer, and there's infinitely many that are coterminal with each of those. So notice that the two answers that we have are half a circle apart. To get from 45 degrees to 225 degrees, you go another half circle. So that would be another 180 degrees, or in terms of radians, another pi radians. Then to get to the next answer, you go another pi radians. Then to get to the next answer, you go another pi radians. So the way to write the answers, all of them together, would be take the first answer and add pi times k, where k represents an integer. So you're going 1, if k equals 1, one more time around. If k equals 2, 2 half circles. If k equals 3, 3 half circles, and so on. So that describes them all. Okay, let's finish up with this. There's a process for finding the global extrema, those absolute extrema, on a closed interval from A to B. Now, we had the extreme value theorem in our first video, which tells us how we know if they exist, but it didn't tell us how to find them. So, what we want to do is realize, if we look at this graph, realize that absolute extrema could occur at an endpoint, like this here is our absolute minimum. They also could occur at a local max or min, like right here we have our absolute maximum. It's occurring not at an endpoint, but at a local maximum. So we need to find all of the local extrema and the endpoints and compare their y values. The way we find the local extrema is we start by finding the critical points, and then we find out if they're, then we find their y coordinates. So the process is, number 1, find the critical points, because those will lead you potentially to the maxes and mins, the local ones. Find the y coordinates of those critical points. Find the y coordinates of the endpoints also, because those are candidates to be absolute extrema. Compare those y coordinates that you found in steps 2 and 3 and identify the absolute max and min. So let's give that a try. Find the absolute extrema of the function f of x equals, look, this is the function we had earlier on the interval, the closed interval from 1 to 4. So we already found the critical points. Remember when we did this problem earlier, we got 0 and 2. Now, only 2 is in this interval, and 0 wasn't even in the domain. So just focus on the critical point, x equals 2. So we need to find the y coordinate of that point. So that would be 1/2 minus 1/4, and that's 1/4. And then we also need to find the y coordinates of the endpoints. So x equals 1 is an endpoint, and x equals 4 is an endpoint. Okay, we have the y coordinates of the critical points that fall in the interval and the endpoints, and now we compare them. Which one is the greatest? Which one is the smallest? So the smallest is 0, so that's going to be our absolute minimum, and it happens at f of 1, or it happens at 1, so you can say f of 1 equals 0 is the absolute minimum. And which one of these three numbers is the greatest? Well, 1/4 is greater than 3/16, so the absolute maximum is 1/4, or we can say it's f of 2. I don't know why, but a lot of students forget about this process, so do something in your notes to make it stand out. Highlight it or something, because it comes up again, and when it comes up again, a lot of students are like, I have no idea what this is talking about, but there's a very simple step-by-step process to follow. Okay, let's do one last example. And by the way, when your book says find the max or find the min, it's referring to the absolute max or min. So problem 7 says find the max and min of the function on the interval from 0 to pi over 3. Okay, now this is the function we already found critical points for when we did problem number 5. So remember, we found the derivative. Guess I don't need to write that again. Just look back at number 5. And we found that the critical points were x equals pi over 4 plus pi times k. Now, luckily, we have this nice small interval. Think of it as 0 degrees to 60 degrees. And the only one of these critical points that falls in there is 45 degrees. So just pi over 4. So let's find the y-coordinate of pi over 4, as well as the y-coordinate of each of our endpoints. Okay, so we have sine of pi over 4. That's the same thing as sine of 45 degrees plus cosine of pi over 4. And remember, the sine and cosine of 45 degrees are square root 2 over 2. You can draw reference triangles for those. When you add those together and reduce, you get square root 2, which is approximately 1.4. F of 0 would be the sine of 0 plus the cosine of 0. Sine of 0 is 0, cosine of 0 is 1, so we get 1. And f of pi over 3 would be the sine of pi over 3 plus the cosine of pi over 3. Sine of 60 plus cosine 60, make a reference triangle. It's a 30, 60, 90. Sine is square root 3 over 2, and cosine is 1/2. And let's go ahead and approximate that. And that's about 1.37. Let's go back to square root 2 again, just to be sure. Square root 2 is 1.41. So looking at those, we can see that the absolute maximum is square root 2. And that happens at pi over 4. And the absolute minimum is 1. And that happens at x equals 0. Were we guaranteed to have an absolute maximum and an absolute minimum? Well, let's see. This is a continuous function. Sine of x is continuous, cosine of x is continuous, the sum of two continuous functions is continuous, and the interval is closed. So according to the extreme value theorem, yes, we were guaranteed to have the absolute maximum and the absolute minimum. Okay, here is your assignment. Thanks, everybody.